Okay, done. Right. Okay. Now, optics and lenses. There we go. Okay. The key learning intentions. There's two types of lenses: converging and diverging lenses, and how this can shift the focal point. Now, students need to understand the following terms and concepts. A convex lens is a converging lens. A concave lens is a diverging lens. I should put that in there, shouldn't I?
Yes.
Because, of course, it is the whole point. There you go. Put that in there. Done. Okay. Now, and then we have the different parts of the lenses and how it works together. So let's have a look at this. This is a pretty famous story from history. Archimedes, you may have, well, in year 7 you studied levers, yes?
Yeah.
Simple machines. Archimedes, he was a mathematician, and it was based on his mathematics that he discovered the principle of the lever. And you go, well, that's not very exciting. But he also invented pulleys. And so he knew about levers and he knew about pulleys. And when the Romans sought to attack the city of Syracuse, where Archimedes was based, he through his inventions, was able to hold the Romans off. When they approached by sea, catapults were throwing things at the ships, and if they got close enough to the cliffs, Archimedean cranes would swing grapples over the ships, pick them up, and then just lift them out of the water and drop them on the rocks. Okay, so the Romans came overland, and the Archimedeans were using catapults to defend the city as well. And it got so bad that, this is recorded, that if the soldiers were approaching and they even saw like a bit of cloth fluttering or something like that, they started screaming, "Archimedes, Archimedes," and they'd run away, which the Romans never did. So they eventually got in the city. They had a general by the name of Marcellus the Sword was driving them forward. The orders were to take Archimedes alive at all costs, because he was a valuable resource. And when he was found, he was sitting in the street, just sitting in the street, literally on the ground, doing mathematics. And a soldier said, "You know, you've got to come with me." He just didn't. And so the soldier stabbed him. And that was the end of him. He was about 78 at the time. But there's one story, and when he was in his 70s, he invented pulleys, and people go, "Yeah, okay, that's fine, fascinating, how is it useful?" And he strung a whole bunch of pulleys together, and he by himself was then able to lift a ship out of the water by himself, using a crane and lots of pulleys. Just walking along, this little old guy pulling a ship of maybe 20,000 kilos out of the water. And he demonstrated the concept then. But he also had lenses and mirrors. So there's stories about Archimedean death rays, where he'd concentrate sunlight and burn the ship's sails and start to burn the water, or burn the people who were on the ships as well. So, now, convex lenses or biconvex lenses, they are a converging lens. They're the fatter ones, the fatter in the middle. So make sure you're clear on that. And you're familiar with them because we use them to focus. We took sunlight over a wide area and we converged it to a point. And what was the point that the sunlight was focused to? The focal point, or the principal focus. Okay, so we can call that one there, if you want to put that in. Focal point is another way of remembering that. So that's what we did with our magnifying glasses. That light concentrated it to a point, the infrared and the visible light, and not very hot, and hopefully the paper burned. Now, biconcave lenses are thinner in the middle with a cave each side, and they're a diverging lens. And you can see when light comes in, it actually spreads away from the lens. Okay? And the way you calculate the angles that it spreads away is you pretend that's a concave lens, you work out where the focal point is, and then using dots, and then your ray moves away from the lens. You'll notice in these diagrams, very importantly, we always have the arrowheads showing the direction of where these rays are going. It makes it clear. You can't have a diagram or draw these images without including the focal points and which way the rays are going. So this ray of light is coming in parallel, these rays of light, and they get brought to the focus. And these ones come in parallel, principal focus that's actually on the same side of the lens. So, thinner middle with a cave each side, they're a diverging lens. Now, a plane, flat mirror, produces a virtual image. The virtual image was this idea that it's an image you can't touch. It's not in this world. It exists in a virtual world behind the mirror. But these lenses actually produce real images. They can be captured, they can be touched, they can be used to develop film. We'll do this later. You'll each get a go at this. Here's my lens. Now, if you look closely, come on, get that right. Where is it? Where is it? Where is it? Where is it? Oh, there you go. There's outside, upside down. I can touch that image. So the image is in the room with us. It's not behind a mirror or something like that. So when you do that, you'll realise, oh yes, the image is there. It's a real image. It's upside down. So if I'm close like that, if I'm inside the focal point, my eye should look enormous, yeah? So if I'm inside the focal point, I get magnification. Is the image right way up or upside down?
Right way.
Okay, so it's larger and it's right way up. If I'm outside the focal point's about here, and those trees are miles away. If I'm outside the focal point, the image is smaller and flipped upside down and flipped left to right. Okay, so that's, we'll cover that in a second. But that's what a real image looks like. Okay, so here's a couple of definitions. The focal point, or the principal focus, where light rays, when they come in parallel, get focused. The focal length is the distance from the centre of the lens to the focal point. So if it's a very fat lens, it has a short focal point. If it's a very thin lens, it has a long focal point. So your eye has a lens in it which has a focal point as well. Okay, but you're not going to be able to get something close enough to the eye to get it to work like a magnifying glass, which would be cool, but that would mean it would have to go inside past your cornea. So unless you want to do that, which I don't recommend. And Newton did something almost as weird. He stuck a poignard in his eye, which is a sharp, pointy blade. It doesn't have a cutting edge. It's just a point. And he put that up and through and under his eye. And was pushing it back and wiggling around to try and work out what vision was. Okay, don't do that either. Yes?
Could he see?
No, he didn't go blind, but he did stare at the sun for long enough that he was unable to see for 5 days. Because for a long time people didn't know what is colour. You know, what is this thing that we call vision? Now, the interesting thing is, the real image that I showed you there, which is smaller and upside down, that's how your eyes work as well. Everything you see is upside down. When the image that gets projected onto the back of your eye is upside down and smaller. And your brain automatically flips it. So, yes?
Why does it flip it?
Because that would not be a good representation of reality. If a tiger is coming towards me, I need to know, where's the ground, where's the sky, and where's the tiger accurately. So I don't want to have an inverted image. That's not going to help.
But would you get used to it?
You might. You might. Yes.
If you hung upside down long enough, your brain flip it around the other way.
Strangely enough, that's not the wackiest question. You can get glasses which will flip the image, the world, and if you wear them long enough, your eyes will get used to it and you'll start to see the world normally. And then when you take them off, everything's upside down. And then you kind of messed up for a while. Okay, so,
Where do you get them?
I don't know, but I heard about it. Okay, there's that. Now, drawings. Quick, highlight this. You need to show parallel lines. These are the rules of the game. Arrowheads on the lines, labelled focal point. If you don't have these, you lose a half mark in each case. So quickly highlight those. So the red parts here, these red things, if it's red, it's important. It can be tested. And almost everything's red. Blue is just background. I'm writing the test. I'm not going to ask you what is a principal axis. That's why that's blue. Okay? Now, a weak lens, they don't bend light very much. So they have a long focal length. Whereas a strong lens, they do bend light very well. And they have a a short focal length. So, you keeping up?
Yeah.
So you finish those? Okay. And so there's just a slight difference in terms. And so in terms of you, in terms of you magnifying, using lenses to magnify infrared and light to try and burn paper, neither of those is better than the other because the surface area of the lens is the same. So the amount of infrared it captures is going to be identical. But if you had a magnifying glass like that, then it would be a death machine. It's really going to... Now, do you need a magnifying glass like that? Or if you had a lot of weak ones, you can get them to work together and focus at one point. And then it's going... And that's what they do with long-range telescopes. Why have one telescope when you can have 20 of them really far apart?
They don't do the massive lens anymore, do they?
No, they don't. They actually have a honeycomb almost effect of glass lenses and telescopes are actually multiple lenses, and then they use computers to marry the images together. So the next generation of telescopes, which they've been building for about 10 years and will be finished in maybe 5 or 6 years, use those ideas. You know, you can only get glass so big, and then it just doesn't work anymore. Radar telescopes are easier to do than visual telescopes. Now, the blueprint is background, but I think you're familiar with this idea. The magnifying glass, okay? Any ray from an object travelling parallel will refract through the principal focus. A ray passing through the centre of the lens is not affected and travels straight through. So if you have a ray of light coming through here, and if you had to draw this picture, so here's the bottom of the pencil, okay? The bottom of the pencil is on the principal focus. The ray of light carrying that information goes here, so I draw my pencil bottom there. Now, here is the pencil tip, and if it comes through the centre of the lens, it goes straight through, and there's the pencil tip. Here's the pencil tip again as a horizontal ray, and if it goes there, it'll go through the focal point and come out here. So that's where I'm drawing my pencil tip upside down, and the image is smaller. So when the object is outside the focal point, you get a smaller upside down image. But if the object is inside the focal point, and I put my eye over here, the way this works is that I get a virtual image. This is a real image. Let's highlight that. I get a virtual image that is larger than the original object. And that's how I'm using the magnifying glass to get this magnification effect. So if I put the object here inside the focal point, I get a large virtual image that I cannot touch. If it's outside, I get a real image that I can touch. And so this is the way we typically use magnifying glasses. We get things nice and close and we go, oh, I'm getting a good look at, you know, whatever it is I'm trying to check out. Now, I think I have the same information on the next slide, but look, a convex lens produces a smaller upside down real image whenever the object is further away from the lens than its focus. No image when the object is placed exactly on the focus, and a large right way up virtual image whenever the object is closer to the lens than the focus. There's this idea again, this virtual image. So there's my eye, there's the insect quite close to the lens, the focal point is maybe here, and what I see is this magnified image of the insect. And so if a convex lens is held near the object looks bigger because the lens bends the light rays inwards. The eyes trace the light rays back in straight lines. It's here, virtual image, that is magnified. So that's kind of useful and interesting. Now, these ones here, for concave lenses, work in a different way. And so here is our object, and we generate a virtual image. So the object is outside the focus, the virtual image is significantly smaller and right way up. So any ray travelling parallel will refract so it appears to come from the focal point. The ray passing through the centre of the lens is not affected. A concave lens always produces a virtual image which is right way up and smaller than the original object. Which for us, probably thinking, well that's not particularly useful in terms of a lens, but of course they do have uses in the real world. But in this case, yes, you do end up with a virtual image that is significantly smaller than the real image. And that's what you're seeing there. And we do have some lenses that are available to us. I'm hoping we can get a hold of those. It's not so much that they're not available, it's the time is always an issue with this course, because we've got quite a bit of work to do. We use 2 classes for the eye dissection, and then we might have a bit of a play with things today with the lenses and do another little mini experiment. But we lose, we use 2 classes for eye dissection, another class for the test, so that's a week right there of the term. And then we have homeostasis after that. Did I change?
Yes.
Okay, that was clear. Okay, magnification can be calculated by dividing the size of the image by the size of the object. Okay, so if a 2 centimetre object produces a 10 centimetre image, how much has it been magnified? Well, 10 divided by 2 is 5 times. It appears 5 times larger than it would normally, which is quite useful. If an object is 8 centimetres high and the image is 4 centimetres, then the magnification is 4 divided by 2 and it is half. So it actually appears smaller. It's not, magnification works either way. We use the same words, we use the same mathematics, but the image you would actually see in this case would be smaller than that. Now, obviously we need to provide some examples of how we go about using lenses, and telescopes is a pretty good example of this. I just found this morning, prior to this class, a simple experiment that someone did where they just used 2 lenses. So you can try this as well. 2 lenses about, oh wow, that actually works really well. I'm shocked. That's ridiculously well. Okay, everything's upside down, sure, but I'm not good at magnification. It's the students.
Does that mean you need 3?
You're upside down.
Am I upside down?
Yep.
Yeah.
That actually looks great.
Okay, so he was a bit more precise. He had a piece of wood so that the lenses would always line up nicely, and then he could do more detailed experiments. But he got a simple 2 lenses to act like a telescope, and then he got 4 lenses over about 4 metres, and he got a pretty good telescope effect. So we'll see if we can do that. But obviously lenses have been used a long time in this way. Magnifying glasses have been around for quite a while. They're used as light glasses to help people with poor vision. But using lenses to create telescopes has only been around for a few hundred years. Now, there we go. Now, this is your cram card. So this is everything covered except for the eye, but we'll get to that. And the key information is there. So these are all the cases where you get a virtual image. Flat mirrors, virtual image. Concave mirror, and concave mirror, and convex mirror all produce a virtual image, as mirrors do. A concave lens and a convex lens both produce virtual images depending on how close you are to the convex lens. But a convex lens, if you're outside the focal length, you get that real image, smaller and upside down. So what are the 2 ways? Long story short, what are the 2 ways to get a real image? This way? Yep. To use a convex lens and an object outside the focal point, and your eye also produces real images. Because your eye has a lens like that in it, and it's taking the images from outside and focusing it onto the back of the eye, which is curved, the retina, and then the nerve cells there, if light is hitting them, they fire and send. So they take a light signal and translate it to an electrical signal, which gets to my brain as the image that I'm seeing. Okay, so that's essentially what your eye is doing. We'll do eyes next, and that's it as far as that particular slideshow goes.